How many of the first 5,000 positive integers are neither perfect squares nor perfect cubes? One way to start this problem out is to ask, what are the first 5,000 positive integers? Well, they are 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 5,000. And some of those numbers in there are going to be perfect squares. Examples of perfect squares are 1, 4, and 9, 16, 25, etc. Perfect cubes, for example, are 1, because 1 cubed is 1, 8, because 2 cubed is 8, 27, because 3 cubed is 27, etc. So let's write out, at least to get these things rolling here, let's write out the perfect squares. Perfect squares are 1, 4, 9, 16, and there will be some number out there that is less than 5,000 that is the last perfect square. One question here might be, how many of these are there? Well, think about the following experiment. If rather than having 5,000 of these, there were only 100 positive integers that you were interested in, you know that you would have 10 perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Well, where did I get that 10 from? I took a square root. So I took the square root of 100. Well, in this case, if there's 5,000 of them, I should take the square root of 5,000. Now, there's a problem in that square root of 5,000 may not be an integer. So if it's not an integer, I want to take the floor of that. So I want to take the next integer below that. And when you take the square root of 5,000 on your calculator, you get a number that's between 70 and 71. So when you take the floor of that, it comes down to 70. There are 70 perfect squares. That's the number of numbers in this list between 1 and 5,000. Now let's go to perfect cubes. Those numbers are 1 to the third power, which is 1, 2 to the third power, which is 8, 3 to the third power, which is 27, 4 to the third power, which is 64, 5 to the third power, which is 125, etc. The question once again is, how many perfect cubes are there? Well, in this case, what you want to do is you want to take the cube root of 5,000, which may not come out to be an integer, so once again you take the floor of that, and it turns out that there are 17 perfect cubes between 0 and 5,000. Now the next question is, have we double counted any? Just like in a problem previously, we might have a number that shows up in this list that also shows up in this list. Well, clearly 1 shows up in both lists, and 64, for example, is 8 squared, but it's also 4 cubed. So let me write the list of perfect squares and perfect cubes. So we know 1 is in both lists. We know that 64 is in both lists. The next number that is in both lists is 729. The next number is 4,096. Now, how did I figure these out? Well, it turns out that 1 is 1 to the 6th power. 64 is 2 to the 6th power. This is the only way they get to be both a perfect square and a perfect cube. They are a perfect 6th power. Our 729 there is 3 raised to the 6th power. And our 4096 is 4 raised to the 6th power. So it turns out 5 to the 6th power is way outside of the range 1 to 5,000. So we only get 4 numbers here. If you wanted a way to figure that out without listing them, as we were able to do here, you would take the 6th root of 5,000 and take the floor of that, and you would get the 4. But fortunately, in this case, we're able to list them all out. So once again, we're going to go to a Venn diagram here. And we are going to have 2 sets. And these 2 sets will be S, where S is all of the perfect squares. And another event C, which will be the perfect cubes. Now we know that S intersects C will be the perfect squares. And perfect cubes. And so these numbers, 164, 729, 496, they fall in both categories. These are both perfect squares and perfect cubes. And we know that there are 4 such numbers. So in this space, I'm going to go ahead and write the number 4, indicating that there are 4 numbers that would be in that particular slice of the Venn diagram. Now, we know that if there are 4 numbers here, and the total for S has to be 70, then we know that there must be 66 that lie over here, so we get 66 plus 4 totaling our 70. Likewise, if we know that there are 4 here, and there are 17 total for all of C, then there must be 13 that fall here. That is, they are perfect cubes, but they are not perfect sixths. Finally, let's add those 3 numbers together. That is, add 4 plus 13 plus 66, and we get 83 when those are all added together. We know there must be a total of 5,000 in these 4 different pieces of the Venn diagram. So if these guys here add to 83, if you take 5,000 minus 83, you will get 4,917. And 4,917 are the number that fall out of S union C. And that is the number that answers the question, because we want to know how many of those first 5,000 are neither perfect squares nor perfect cubes. That's the number that fall outside of here. So the answer to the question is our 4,917.